I'm almost certainly about to draw all those exact same diagrams again, but that's anyway. Okay, so the first part here, the idea was really that you've given some information here, which is the various constants and things that each molecule has that you can't calculate easily from first principles. And then you can use those and look for the right formulas and things like that in the notes, you can just to calculate these different quantities. But it's, I realize, yeah, but maybe it's not completely clear what all the quantities physically signify or how the formulas, what the formulas mean. So I thought we can do an example of that. So, first of all, so these constants describe the molecule and the way it interacts with this environment. These two are the ones you need to work out the energy of the molecule. So that's first of all, you might wonder why is this, say, centimeters when it's in energy. And the thing to remember is that if we were talking about a photon, then its energy is proportional to its frequency. If we have Planck's constant, which is just a fundamental constant of the universe, it never changes. So if you ever know the frequency, you always know the energy. They're equivalent, basically. Alternatively, you could say that the energy is equivalent, also can be written in terms of the wavelength. And now we have the speed of light, another never-changing constant of the universe. So if that's wavelength. So meaning that whatever the wavelength is, you always have a discrete energy. So you could use wavelength to describe the energy as well. Reasonable. There's another quantity the wave number, symbol nu, and that's just 1 over the wavelength. And you might wonder why it's called the wave number. Well, if you have a wave, and say this is 1 centimeter, then you could say that the wavelength of this wave is 1 centimeter. And the wave number is the number of waves in 1 centimeter. Alternatively, if this was 2 centimeters, then the wavelength is 2 centimeters. The number of waves in 1 centimeter is 0.5. So it's kind of counting waves rather than measuring their length. Anyway, the point is that you can then write the energy in terms of the wave number. And once again, these are just fundamental constants. So writing the wave number in terms of how many waves fit inside 1 centimeter is equivalent to the energy. That's the reason. Okay. Sorry, I'll have to rub this bit out. Okay, so the first part of this question, A, is to calculate the energy levels. And there's only 2 energy levels in this problem, J equals 0 and J equals 1. And so the energy of the J equals 1 level, if you look at the formula, is there. And so I've given both these numbers, B and D, in the information, so that, and J, you know, is equal to 1, J equals 1. So we have an energy. And for J equals 0, that J is a 0, and that J is a 0. So whatever happens, that's going to be 0. So that's not actually a difficult calculation. And then the next question is, what is the frequency of a transition of a photon that results from this transition from the continuous to J levels? The energy that the molecule loses is the same as the amount of energy that the photon gains. That's conservation of energy. And so we now know what the energy is that the molecule loses, and we can work out what the wave number, the frequency wave number of the molecules as well, with these fundamental constants, which so I didn't include those on the sheet. You might look those up on Wikipedia, or look in the Python constants package. That's a good place to find these fundamental constants. So once you know E1 and E0, the change of energy when a photon comes out is just the difference in the energy from this diagram. So that's that part. Okay, the Einstein A coefficient and the critical density, that's deeper in the talk, in the presentation. So I'll leave that bit. Maybe someone asked me about that later. I can do it on the board, but maybe I'll leave that. Because the more confusing part, I think, is when we get to this part, the excitation temperature. That kind of is the thing, I think, that is not quite as intuitive when you have a two-level system like that. I will erase this. First of all, does anyone have any questions about this part of the problem? Nope. Okay. I'll make one more comment quickly. If I write it again, the energy in terms of the wave number. The main problem with this is the energy is often given in joules, but in our case, it's given in inverse centimeters, in our case. And this is in inverse centimeters. So generally, you're in pretty good shape to get the units right. I mean, if you consider these, if you keep the frequency in inverse centimeters, the energy in inverse centimeters, you're kind of calculating the same thing. On the other hand, if you want to know the frequency, equals C over lambda equals C nu. This is probably going to be in gigahertz, so that's 10 to the 9 per second. And this is going to be in inverse centimeters, centimeters minus 1, neither of which are MKS units. So there's some powers of 10 in that part, which can be tricky. Anyway, okay, so the problem in spectroscopy is to work out these energy levels, to work out these frequencies, the energy difference, and then to deal with the populations. And one of these questions is about calculating the population, which if I assume you've done that, which might be some work I appreciate, but we'll worry about that later. Okay. Then, so the thing we're interested in is if there's three molecules in J equals 1 and 2 molecules in J equals 0, what does that tell us about the temperature? And if you draw a curve, then in this case we have 2 molecules in the first level and 3 in the second, giving us 2 points on a function of rotational level per population n. Maybe if we had more than 2 levels, we'd also conclude some other states. And because we're dealing with quantum physics, there's only discrete levels, so there's only points we can draw, although we could, in principle, draw a curve connecting those as well, just to make it clearer the shape of it. And the shape of this curve, how many levels are in each level, depends on the temperature. That's something in the notes. The question is, if we have, that's a high excitation temperature. If we have a low excitation temperature, then we have more molecules in the bottom level and fewer in the top level. That's the definition of temperature, how much energy the average molecule has. So that means we have a situation now where there's 1 here, 4 in the first level, 1 in the second, and probably 0 in the rest. So we have another curve which looks kind of going down really quickly. Lows. And so this is what we're looking for. Even though we're only looking at the first two levels in this problem, the ratio of these two levels, that level to this one and that level to this one, that difference actually tells us what the rest of the levels should look like. That's why the temperature is useful, because it gives us a distribution of all levels just by looking at the first two. Because this function has a formula the exponential going down, that's what makes it go down here and go down over here. A constant, which in this case we're not going to use at all, so that's the partition function to do with just the general picture of the molecule, and the degeneracy. And that's the part which maybe I didn't explain so well, actually. Because this picture is not completely accurate. I'm going to draw it again, sorry about that. I should really draw it like this. Because if a molecule is in its J equals 0 state, it's not rotating. There's one way you can have a molecule not rotating. Seems obvious, but so if there's there's two atoms in the state, they're both not rotating in the same way. If you have a J equals 1 molecule, there's three ways for a molecule to rotate with J equals 1. That's the quantum mechanics to do with the fact that you have to have a whole number of waves, but in more than one dimension now. It makes that more complicated. So the three molecules that have this rotational state could be in any one of these three ways to rotate with J equals 1. And in fact, there's a formula. If J is equal to n, then the degeneracy is equal to 2n plus 1. That's the formula. So the more energy you have, the more ways the molecule can rotate with that value of J. It's a strange concept, I know, but it's exactly the same as if, I don't know, I'll think of a metaphor later. So that's this value. And what that means is that here we have an exponential e to the minus e to the minus e. And you have higher and higher energy as you go up in rotational levels. So e to the minus e looks something like that. G, the degeneracy is equal to 2n plus 1, 2j plus 1. That's a linear function. And the whole function is equal to g times this one. So that's why you get a shape kind of like that. This is the function I drew over here. So that's given, there's kind of a reason why it goes up and then down again. And I kind of waffled on a bit about the similarity between particle velocities and radiation fields. They all have the same property of energy and exponential and degeneracy to do with the number of ways you can do something. Anyway, okay. So we can ignore any questions about that idea. Exactly. Okay, so in the question, we're not trying to calculate nj, actually. We're trying to calculate n1 divided by n0. So that's the nj of this level divided by the nj of that level. The advantage of that so that's that function divided. There's two values of j now, j equals 1 and 0. So we can cross out the 1 over z. Like I said, that's not going to be a problem in what we're dealing with. And we can combine the exponentials using the rules of exponentials. Okay. And then we get the formula which is in the presentation about this exact problem. The ratio of these two levels, in this case it's 3 divided by 2, I'm counting that problem, equals the ratio of the degeneracies, So yeah, 1, yeah, sorry. So the degeneracies, which is 3 divided by 1 times the difference in the energies, which I've rubbed out, sorry, but the energy was 0 and 1 point something. 1.46 wave numbers. 1.46 minus 0 divided by Boltzmann's constant, which in these units is 0.673. That I think was in a previous test, but I'll make a note of it somewhere as well, times excitation temperature. Okay. So basically, by considering this formula, the results about what these level populations are, we can put in all the numbers except for the excitation temperature. And so this is an equation you can solve for the excitation temperature. And that, I think, is the question. What is the excitation temperature given by these ratios? And this is the way to do it. And yes?
Excuse me. To which molecule does that rotational energy correspond? 1.46.
Yep. Silicon oxide. So it's not the same as there's some other constants for that molecule, yeah. Yeah. And I'll stop talking there because I talk too much. But are there any more questions about this part of the problem? Yes?
Didn't we forget the Boltzmann constant?
I did here, yes. Sorry, you're quite right. And I forgot it almost everywhere except here. I wrote it in at the bottom. Good point. I mean, in some ways, it would be easier if we just express temperature as an energy directly. So Boltzmann's constant was 1. Then we'd be in a room with a temperature of 10 to the 20 joules or something, whatever the Boltzmann's constant is. So on a hot day, it's 11 times 10 to the 20 joules temperature. Anyway. Any other thoughts about that? Mm-hmm. Okay, well, please work on the exercise. Like I say, asking me questions immediately is good because then I can explain it to you or maybe do some more work on the board as well. And the answers are really, they're kind of numbered. And so the simplest way, if you like, is to return the test is if you write a document or a text file, write in the answers with the numbers and a few words, if you think a few words will help understand. But the main thing I'm interested in actually is later in the test, there's some graphs and some explanations about the physical effects. And the graphs I think are very interesting because they summarize all the parts of these equations in one picture. And also the discussion is to do with the physical conditions with clouds and things, so that we probably need to talk about. So the point is that if it's making no sense, rather than think about it for too long, I mean, ask me or ask somebody else, and the idea is that we can work it out actually. Thanks for listening. What did I do? Ah, that was the picture I drew here, 1, 2, 3, and 2. So the degeneracy is fundamental, but the formula really, the idea is that if you increase the temperature, this number becomes smaller and smaller, so bigger and bigger, because it's e to the minus, and that's on the bottom. And so this ratio will become 3 over 2, 4 over 2, 5 over 1. There's more particles in the upper level. But the actual question is not to do that, but to go the other way. Start with this and work out what the temperature is.
More details so they can.
Yeah. I think there's no limit to how many details are useful. I think actually.
I thought that was too bad because once you open cards, there will be the years that you play, but of course, there's some surprise.
Yeah, you want an objective